Hello from Dendrite Digital in Anaheim, makers of the Virtue Data Processor, and ZipBits, the website that shows you how to use JavaScript, HTML, and CSS. Today I'm going to show you a new Verilog program that I've written for the Nexus Video FPGA. I'm going to show you the code, and then I'm going to show you a demonstration of what the code does on a VGA screen. It's 8 bits per pixel, 640 by 480 pixel screen, and it's all coded and available on GitHub. Link is in the description. And so that's timescale. And then this little line I have here, it turns on and off things that are between the if-def and end-if. So you can select parts of your code to run in simulation and then take the simulation code out by commenting out this little line here. And that way you can turn on and off your debugger. You can also use that to turn on and off your parts of your code that display things to the console. So, this first part here that's been commented out by the debug, that's a unit under test. That allows me to view the waveforms of the various inputs and outputs. And they're all outlined here. So the first one, of course, is clock. That's your system clock. The Nexus Video uses 100 megahertz system clock. So that comes in as CLK. I don't know why they stuck with that, but you know, it should actually say clock, CLOCK. But I think the industry standard just abbreviates it that way. And then I have a PLL, which sets the clock to 3 times the pixel frequency of VGA pixel frequency. So that's roughly 75, but it's also 0.525, and that's to get the pixel frequency exactly right, so you're not destroying your monitor when you have bad timing. Everybody that I know of sets the clock to 25 megahertz. And that's a mistake because it's 25.175 megahertz. And they just set it to 25 megahertz in order to avoid making a PLL. They just divide the clock by 4. And it works, but on some older monitors you might damage them that way. So that's 3 times the pixel frequency, almost exactly with the PLL. So I get a very precise screen out of that. And then timer, this just counts how many clocks per pixel. And then write, of course, I want to write data out to memory, and then I want to read it in when I'm displaying pixels. So I just use write to initialize it, initialize the RAM, and then it just cycles through the screen over and over, doing the same screen. And you'll see later that I initialize the screen so that it has an even odd scan line thing. Basically, I took every permutation of the palette, 0 through 255, and I cycle through 0 through 255, And of course, that doesn't quite go evenly into 640 pixels. So every other line is interlaced, and you'll see the pattern. I'll show it to you at the end of this, and then yeah, you can skip to the end of the video and look at it, and then come back and look at the code. But I'll put it at the end, and then so pixel address is the address of the data that we're getting the pixel data from. And of course, this is 17 bits, not 16. You need about 75K times 32 bits to do a 640-480 screen. So you need at least 307,200 bytes of information to get a full 640-480 screen of 8 bits per pixel. Pix out is the data going into the, I don't know. We'll look at it later. And then vcount is the number of what scan line it's on. And of course, there's overscan. There's a horizontal blank and a vertical blank. Those are managed by hsync and vsync. And then we have VGA red, VGA green, and VGA blue. 4 bits per color channel, so that's 12 bits total. And this is just matching the ports for the VGA unit. And here we're initializing the clock, and we're waiting 100 cycles. That's the pound with the 100. That's this right here. It's basically 100 nanoseconds. So that's waits what? Waits point 0.1 megahertz. And then this is 100 megahertz here. The pound 10 is 100 megahertz by our time scale. You have to have that. Yeah, this is a pesky thing. The little single quote right here. If you're in a yeah, you go single quote, and it does 2 of them. And Verilog only uses 1 to denote compiler directives. So, strange thing there. And then, here's the quote end if, or hyphen, I don't know, accent mark, I don't know what that is. End if, and end module. So in Verilog, you start each module with module. You have ports. Here we're doing a unit under test, so it's a little different. And you have your ports, output ports, input ports. You can have in-outs as well, which are bidirectional, and you have to treat those very, very carefully because on one end you want to receive, and on the other end you want to transmit. And when you're receiving, you set the you assign Z, which is high impedance, and that prevents the output signal from interfering with the input signal. And then so here clocks per pixel. We're using timer to count the cycles per pixel, and it needs to know how many clock cycles it needs to delay for. So clocks per pixel. Horizontal sync polarity. Now that could be 1 or 0. In VGA, the standard is negative polarity. So when this goes to low, it's doing the sync pulse. And then horizontal front porch. This is the time for the horizontal scan line to be high before it does the sync pulse. And then back porch, that's the number of pixels from the far left until that ends, and then it becomes the visible area. So actually that's the pause between the sync pulse and the visible area. And then the difference between front porch and back porch is the sync pulse duration. So that's what, 96 clock pulses or pixels. It's not pulses. It's not the clocks per pixel. There's 3 of them. So these are pixel relationships. They're not clock relationships. Otherwise, these would be 3 times bigger to match my 75 megahertz clock. So I use all of these defined parameters. I should probably use parameter, but I like using defined. And these set up the various timing signals for the graphics processor. And so horizontally, we're only displaying 640 pixels, but the total width of the line, including the sync pulse, the front porch, the back porch, and the whole thing that's blank, plus the visible area. So I have this is unusual. I haven't seen anybody do it the way I'm doing it. I'm putting the all the blanking for both horizontal and vertical in the upper left corner. And that way I can prepare for the frame. And I can use the total width as the end of the visible area. And it allows me to remove at least one if statement, one if condition on every parameter. And I found it's really cool because you can set up your display area with data loads before you start displaying things. So there's that. And then, of course, we have the sync polarity for vertical, which is the same as horizontal. But I'm told that it's part of the standard of video signaling to you could have different polarities. I haven't seen it done in any specification yet, but you could have a different polarity for the vertical sync pulse than the horizontal sync pulse. And these could be either 0 or 1, just 1 bit, and it has a transition, and then it's doing the pulse, and then a transition turns off, and the rest of the time the signal is the opposite of the polarity. So there's that. So front porch, vertical front porch, vertical back porch, vertical time total blank, and then visible area, and then total height, vertical total height. And then here's actually the code that see, I have another one of these if def debug. See, all of these parameters are in the unit under test, but I don't want these parameters to be in here when I'm putting it on the FPGA, because that's just too much data. It doesn't need to be there. And so all I have is a clock, VGA red, VGA green, VGA blue, horizontal sync, vertical sync. And since I'm doing 4 bits per color channel, each of these is just 4 bits. Most systems, modern systems, they have 8 bits at least for each of these channels. That's 24-bit color, and you have to pump out lots of data very quickly when you're doing high resolution graphics. So, and I'm using a VGA port. The Nexus Video has HDMI ports on it, but I looked into how to code that, and it had transition minimized differential signaling, TMDS, and what they're doing is they're trying to eliminate any DC bias by flipping the bits on and off, so that there's not more than 5 consecutive bits of 1 or 0 to DC bias the cable, and that way you prevent signal loss, because there's no second guessing as to which value it is. Is it high or is it low, or how long has it been there, and any noise that comes in when it's sitting at one value, you'd easily mistake it for a change in the bit. So there's that, and since we have this code here in my unit under test, and it's not here when I'm putting it on the FPGA, I have those same ports here, so I keep my data consistent. And see, this has the little N right there, and that's not defined. If not defined, debug, then it does this. So then there's our 12-bit color, and I have 4 pixels in a 32-bit register, and I divide that down to down here, quad QP, quad pixels. So I put pixels in, I put the column I'm on, and then this outputs the pixel. So here we are. Looks like we have a few spaces with too many here. I like to line up my code. I don't know how I changed something last minute, and it's changed my formatting. So this used to say red, and this used to say green, and this used to say blue, and now I just used the initials. So here's my assigns. I'm using wires for all of these. If you use wire like all this stuff here, then you have to assign it to something, and that assignment happens continuously. So when, for example, when color here changes, it's instantly stuck into VGA R. It puts it in continuously. It's like flowing through the chip the whole time. And so if you have a reg, you can put that in. And if you wanna like count the pixels, I have X and Y. So we take the horizontal total blank, and we subtract it from the position, and that way I can stick the pixel position from 0, 0 in the upper left corner of the screen to 640, 480 on the lower part of the screen. So this is vertical total blank, and that's taking it from vcount. And then here's my PLL. This is the system clock, CLK, and it's going in. The PLL, the clock wizard helped me create a PLL for a specific chip, and that's the Arctic 7 200T currently, and so I'm using the same clock in the RAM, and that here's right, it's active low. It doesn't say that here, but it's active low. And then here we have the pixel address, and here's the pixel out, and here's the pixel dat. And if we go up here, see we have pixels. So pixels goes in here. Later we'll take the pixstat and we'll put it into the pixels, and we'll select out of the pixels the 0 through 3 column, and it'll output just one pixel. And then that we use to set the color at the right time. Okay, so it's important to initialize all your regs. You'll see here, all your regs, everything that says reg, you must initialize at the beginning of your code. And then always use always. That's what my professor said at Cal Poly. And he always said always. Always use always. Professor Yi Chang at Cal Poly Pomona. And then positive edge, megahertz 75. See, that's 3 times the pixel frequency. Gotta remember that. I'm not using 25 megahertz. I'm using 75 megahertz. And then put a begin after that. If you're going to have more than one line of code, you have to have a begin. And then here we're checking to see if it's right. And this is how the data goes from the H count, B count, and data coming in and out of the RAM. It's all done in this situation here. So we have H sync. See, that's the H sync signal, and here's the horizontal sync polarity. Horizontal sync polarity, and then we invert the polarity when it's not after the front porch and before the back porch. You're gonna have the sync pulse, and here's not sync pulse, and we do that for horizontal, and then the vertical. See, we're going from the front porch to the back porch with our synchronization. And then here we're counting the clock pulses per pixel, and we're just adding one to the timer. And when timer equals the sync pulse, then we set the timer to 1. We're not counting 0 here. If we're counting 0, it would be too many. So you set the timer to 1, and then here we have the horizontal count, horizontal total width. So when it reaches the right edge of the screen, it's gonna go to the next. If it's less than the total width, then it's gonna add 1. And here's a debugger. I'm just checking to see if the Y position and the X position, the Y position is 3 and the X position is 8. When that happens, it's finished. And that's for simulation because it's in the debug. And then horizontal count equals 1. We're not counting 0. That's so all of our numbers work out to be what they're supposed to be and not 1 less. Because if we were starting from 0, it would all have to be 1 less than the right number. And I'd rather use the correct numbers. That's all of the see, all this stuff I set up so I can just change the numbers here, and I can have a whole nother resolution, a whole nother type of screen to put my data through. Just change it here, and it changes everywhere in the code that you have that. Just like the debug, only it's got a number on it. And you can make those any you can make these defines any line of code or whatever you want to do in these defines. You don't have to just use numbers. You could use whole if statements if you wanted to. If you could fit it all on one line, you could do it that way. And it would make your code really readable, like I have here. And so here we're adding 1. If it goes to the next line, then we set the horizontal count to 1, and we check if the vertical count is the total height. Vertical total height. And if it's less than, you just add 1 to it. If it's equal to it or greater, then we're going to do vcount equals 1. Again, not counting 0. And we set the pixel address to the negative 17 bits. So you take a 0 and you flip it over with this little tilde here. You flip it all from 0s to 1s, and it's 17 bits wide. You have to tell Verilog all the number of bits for all your constants. These are 10-bit constants. This is a 10-bit constant. This is a 17-bit constant. So I have 17 bits of address. You're going to need all those. It takes more than 64 bits. Or 16 bits, because 16 bits is 65,536. You need 17 bits because you're between 64K and 128K. You're at 75K for an 8-bit screen. 8 bits, 640, 480 is 300K bytes. And I'm using 32-bit numbers to do my pixels. So I use 32-bit numbers. I divide it into 4 different segments. You'll see that later. So here we're checking the debug again. Here's another debug set of code. And you can put anything between the if-def and the end-if. And remember to put the little accent mark, and don't leave the, when you do those accent marks, they want to give you this extra one at the end, but it's Verilog, so only do one of them at the beginning, and don't do it again. Yeah, I suppose you could carry that accent mark all the way down here and then go through it. But text editors, what can you do? And then here we're looking to see if vcount or hcount is less than the total blank for vertical and horizontal. And if either one of these is true, then we want the color to be 0, so we're not drawing outside of our visible area. And if both of these are false, then we're going to draw a pixel to the screen, color equals palette, and see we're using pixel. There's no S at the end of this. If this had an S, then we'd be doing 32 bits instead of 8. And so we have a palette. Let's see if we defined our palette up here. Palette. There it is, palette. So we're doing 12 bits per color, and we have 256 of them in our palette. I'll show you that soon here. So here's the palette. We're selecting an 8-bit number with pixels in 8-bit number. There's 4 of them in 32. And we just select from palette the color. And then down here, if vertical total blank, if vCounter is greater than or equal to vertical total blank, and the X is less than horizontal vertical visible area. Horizontal visible area. If X is less than, you might think that's kind of strange because we had all of that data on the left side. But we're subtracting that number from, we're subtracting the total blank, we're subtracting that from H count, and these are unsigned numbers. The default is unsigned numbers. If you want signed, you have to use the directive signed when you define your variables, your registers, or your regs. And that way, when it's negative, it's not less than this. It's greater than, because there's no sign bit. There's no sign bit at the left side of the data, and so it's a positive number, and it's bigger than 0. And so it's much bigger. It's bigger than 640. So that's what this is doing, is it's checking the horizontal 640 to X, not H count. And that way I can tell if it's on the visible side of the display. And then let's look at that a little closer, because it's kind of a tricky thing here. So we're subtracting the horizontal total blank from H count, and then we're doing the same for V count, vertical total blank, and see we have X and Y, and so we're doing some tricky binary math here to get this done right, so I can eliminate one of my if statements, one of my if conditions. See, because if we had, let's say, front porch on the right side of the screen, sync pulse, and then horizontal or horizontal and vertical back porch on both sides of the screen, you couldn't use like the after the screen and before the screen, and you're losing out on that right side some precious time that you could use to load data in the blanking areas. You can load all your data in the blanking areas, preparing for the screen data. And I just found it better to shove all the blank to the left and to the top, rather than having it on both sides and on top and bottom and left and right, and then you're just all confused as to where everything should be. I shifted it all up to the upper left, and as the screen is drawing, it goes from upper left across horizontally to the right, and then it goes down a scan line, and then it retraces it. It goes over and over, like you're reading English, and left to right, top to bottom. It draws the screen at an incredibly fast rate, especially for these high resolution, high frame rate monitors that they have now. Ridiculous. They're doing 8K. They're doing 8K displays. Too damn many pixels. Too hard to keep up with. And they're doing it for no reason. They're just trying to make more money by giving you, ridiculously high resolution with ridiculously high frame rates and much larger screens than they ever had before. When they were all cathode ray tubes, you'd have this gigantic piece of glass with a vacuum in it, and electron guns shooting pixels at the screen, making the phosphors glow. Oh, how it changed. How it's changed in my lifetime. And so here we have a debug statement. We're just checking to see what the X and the Y and the color and the actually that's the pixel address right there. That's the palette address for the pixel. And so we got all that figured out, so we can in the simulator we can look at it, and here we're actually checking to see if the timer is 3, which means it's the last cycle for that pixel, and then it's making sure that X is on the fourth pixel actually. See, 2 bits, 0, 1, 2, 3, and when it's 3, you're at the 4th pixel of the last clock cycle, and you change your pixel data, and it's using the previous address. See, we're using blocking assignments. We're using blocking assignments. That way, order matters. And so and then right after we set the data, we advance the address. And that way, the address going out to RAM is going to have the right data coming in when it comes around the next time. So there we have it. And here, remember we had if right equals 1 is this stuff. And this is all when it's displaying. When it's initializing, see, if I come up here in my initialization procedure, I set right to 0. So when it begins, it's active low, it's going to write on 0. And down here, there we are. See, we're adding 1 to the address. Remember, I started it with -1, which is all ones. I know it doesn't sound right, but it's all ones. You add 1 to that, it flips it to all zeros. So there's this little trick. The PLL does a tiny little clock pulse before it's ready to run. It's just setting things up. It does a clock pulse and it watches your incoming clock and then times itself to that. And then it generates a higher or lower frequency depending on how you use the clock wizard. And so I'm eliminating that possibility that I'm starting at a wrong address. And then here picks out when this equals 255, the low 8 bits of clock out picks out equals 255. So let me go back to that initial procedure again. So remember I told you about how I wanted each successive palette entry goes from 0 to 255 and then it cycles. Well, I'm doing 4 pixels at a time. So the first 8 bits is 0, second 8 bits is 1, 2, 3. But down here in the initialization procedure, I'm adding 4, 4, 4, 4. Isn't that tricky? So it cycles through all the permutations. 1 pixel at a time is each successive value. And then add 4 to them on the next cycle. So that and here we're just adding 1 to the address. So we're just going to cycle all the way through all the addressable space until it equals that number again, -1. And then it sets the right pin to 1 and the pixel address to 0, and then it starts all over. And then it relinquishes control of the initialization procedure and does the display procedure. And down here, here's our palette entries. It starts at white, and it takes out one value. This is so I can bug test it. I can see in the debugger, in the simulation, that it's changing by 1 each time, and where it starts in this list and what it does. And that way I can look at the data coming out of the display statements and see that it's doing the right color at the right position on the screen. And here we go. So these are all 255 palette entries entered manually. I didn't write a program to do this. I probably could have, but I thought 255 ain't too much. So, and then here's the RAM. This is kind of tricky because later I'm going to make this dual port RAM, and fortunately the code for doing RAM isn't too complicated, at least not as a single port. And here we have the RAM clock, and then we have RAM write, and then we have RAM address, RAM in, and RAM out. And can I scoot back to where I instantiate this RAM in this procedure, just to review here. So up here, here's RAM. So remember, this was RAM clock, RAM write, RAM address, RAM in, RAM out. So if we come back down here, RAM clock, RAM write, RAM address, RAM in, RAM out. So how do you do RAM? It's a good question. This is an SRAM. It works every clock cycle, and I'm told it needs to be synchronous to be needs to be synchronous in some way, and use register to become block RAM. So this way, I have 17 bits of address, and this is 2 to the 17th power minus 1 to 0. So that's your full width of RAM that we have here. And here we initialize it. Every time you use a reg, you must initialize it. Otherwise, it won't work. It'll have X. It won't have Z. It won't have a 0. It won't have a 1 anywhere in the bits. It'll have an X. I won't know. Of course, this is too many regs to fix right away. So I have that initialization procedure. Remember the initialization procedure right here. This goes through every single address in 17-bit address, every clock pulse. It takes the picks out, which becomes the RAM in, and then down here, when write is active low, RAM in goes into RAM address. RAM address. See, that's this number that it's putting in here. RAM address into RAM. And then here's the little procedure for taking the 32-bit 4-pixel unit of data, figuring out what column it's in, 0 through 3, and then outputting an 8-bit pixel. So here's our 8 bits. It's a wire. Yes, it's a wire. I'm not using a reg here, so it's probably distributed RAM. Wire, 8 bits, and there's 4 of them. 3 through 0. And here the 0 column has the upper 8 bits. The 1 column has the next 8 bits. Column 2 has the next 8 bits, and column 3 has the low 8 bits. And that's pretty much all the code I have. And this I've gotten to run flawlessly on a Nexus video. So here we are. And I'm going to just show you the demonstration of my screen in just a moment. Thank you. So here is the VGA screen. If you get up close, you might be able to see that it's interlaced. It's doing one bit different on 12-bit color all the way across the screen, and because 640 doesn't line up with 256 exactly right, it does another screen below that, another scan line below that that's different. So it's going back and forth between the two alignments of 256 colors. So you can see it's doing these brown bars like 5 times. And if you took 640 and divide it by 256, you're going to get about what? 640 is like what? 320, and so halfway is 320. And so it does this alternating pattern back and forth. Every scan line, it changes its alignment. And all it's doing is it's just showing each color out of a 256 palette across the screen, and all the way down. And so here it is. The display cord comes out of the display across the floor and over here to the Nexus video right here. So there's your proof. I'm getting VGA 8-bit video out of VGA 8-bit video out of an FPGA. Thank you.